So let me ask you a question. Do you guys like surprises? Well, sometimes or rarely, but once in a while, the diploma can be full of surprises, and sometimes they, in fact, dwell on surprises so much that they teach you something or expect you to know something that is outside your curriculum. Well, this video is for just that exact instance. What happens if we come across something on the diploma that you don't see in any textbook, any review book, any diploma prep sessions, or even in class? Well, this video we're going to cover the three topics that tend to show up once in a while, and in case they do, I want you guys to be prepared for it. So the first thing that we're going to talk about here is the three subcategories of alcohols, mainly the primary, secondary, and tertiary alcohols. When we say primary, we're talking about an alcohol or a hydroxyl that is on a carbon which just has one other carbon next to it. When we say secondary alcohols, we're talking about the hydroxyl on a carbon that is between two carbons. And when we say tertiary, we're talking about a hydroxyl group that is on a carbon which has three carbons between it. So, how is it going to show up? Right? What does this mean, or how does it show up? Well, let's say I look at the following question here, where we ask you to identify each of these alcohols as primary, secondary, or tertiary. Well, when I look at the first one over here, I've located the hydroxyl. I can see that the carbon that it's attached to only has one other carbon beside it. And so when we look back at the definitions at the beginning of the video, this means that it's a primary alcohol. And we knew that because there was only one other carbon beside it. Now, if I go to the second one, where I've located the hydroxyl, and I can see here that it's on the third carbon. I got propan-2-ol. And the second carbon, I should say. This carbon has two other carbons beside it. And so because it has two other carbons beside it, we're going to call this a secondary alcohol. So I've located the hydroxyl, and then once I've located the hydroxyl, I looked to see whether that carbon in particular had one or more other carbons beside it, and that's how I made a decision. So two carbons beside, this is a secondary alcohol. Now, let's look at the third one. Looks very similar to the second one. I've located the hydroxyl. It is on the second carbon of the parent chain, but when I circle each carbon, I can see that there are three carbons that surround it. Two of them are part of the same parent chain, but one of them is a methyl group or a branch. And so because there are three carbons attached or beside the carbon that has the hydroxyl on it, this is a tertiary alcohol. Now I'd like you to try the next one, and remember, locate the hydroxyl group and see how many carbons it has that surrounds it. So once in a while they have a question that asks you, and usually it's in the form of multiple choice, which one of these organic sets or sets of organic compounds is or belongs to a homologous series. When we call something a homologous series, we're talking about groups of carbon compounds or organic compounds that have the same functional hydrocarbons or functional group or family, but they differ in the number of C's. So when we look at this one, for example, we can see that each of these belong to the alkane functional group. So they're all part of the same functional group. However, their carbons are what differ. What we can expect is that these ones would behave similarly in the lab, but not the exact same, and they would have a predictable pattern because they all belong to the same functional group. And because that's the case, we can say that these are homologous series. So methane, ethane, propane, and butane, because they're all alkanes, belong to a homologous series. Now, when we look at the second example here, are the following compounds in a homologous series? We can see that I've underlined what appears to be the common functional group between them. And the OOH is symbolic of the carboxylic acid functional group. So the first one, since it only has one carbon, is methanoic acid. The second one, with two carbons, is going to be ethanoic acid. And, of course, the third one, with three carbons, is propanoic acid. Now, these all have the same functional group. The only thing that differs between them are the number of carbons in each compound. So, because they have the same functional group, we can expect that they're going to behave similarly in terms of chemical properties. So, because they're all the same functional group but differ in number of carbons, we can say that these are in homologous series. And finally, let's look at the last example here, where it doesn't look like they share a common functional group. The first one is an alkane, one carbon makes it a methane. The second one with the double bond is an alkene, so it's different than an alkane, and since it has two carbons, it's an ethene. And then the last one is propan-1-all, or it's an alcohol. And so do these belong to the same functional groups? The answer is no. So are they in homologous series? The answer is no. Remember, a requirement for organic compounds to be in a homologous series is for them to share the same functional group or to have a common functional group while differing number of carbons. Lastly, once in a while, they might ask you to calculate percent ionization. Now, we've talked about this concept extensively in terms of strong acids fully ionize and weak acids do not fully ionize. But we never actually use an exact number. When we look at Ka values, we usually just say it's above or below 50%. Well, if they give you an H plus value or the means of an H plus value through a pH, let's say, and you have the concentration, we can actually figure out the exact percent to which it ionizes. And although it is rare, it is something they could ask you to do. So using this formula over here, to find the percent, we take the hydronium concentration of the H+, and we divide it by the original concentration of the acid, and both of these are going to be in moles per liter. Then you multiply that ratio by 100, and you're going to get a percent. That tells you how much this acid has ionized. It should always be less than 100%, because we're not going to ask you this about strong acids. We're going to ask about weak acids, and weak acids do not fully ionize. So we should see something below 100%. Let's look at this example here. A 0.25 moles per liter acetic acid has a pH of 3.54. What's the percent ionization? Well, I don't have an H plus directly, but I can get the H plus from the pH that was given. As remember, the hydronium concentration is just the exponential function of the pH, or the inverse of the pH. So we can go hydronium is equal to 10 to the negative pH, and with that we know that it's 10 to the negative 3.54, and when we plug that into our calculator, we get about 2.884 times 10 to the negative 4 moles per liter. Once we have this hydronium concentration, we can then use the percent ionization formula, which is going to be our hydronium concentration divided by the concentration of the acid given in the question, multiplied by 100. In this case, the hydronium concentration is what we just found out, 2.884 times 10 to the negative 4. And we're going to divide that by the concentration given in the question, which is about 0.25 over here. And then once we've plugged that in, we're going to multiply by 100. And it is a weak acid. Acetic acid is a very weak acid, and that's a low concentration. So we can expect a low percentage. And so you're going to plug that in. Once you do that, you should get about a 0.11%. And I was just checking the digits there, so it's actually 0.12%. And that is extremely low, but not uncommon for weak acids.